Hello everyone! Today we're dealing with vector applications, and this topic is dedicated only for a higher level. And as always, we'll go through some exercise to make sure that you understand every type of question. So let's get started. Problem 1. A line L is defined by vector r. A point P with coordinates 4, 1, 0 is given. Show that P does not lie on L. So simply we have to substitute this point into our line L. So this point has to be substituted as vector r. So 4, 1, 0 equals 2 minus 1, 3 plus lambda 1, 2 minus 2. So we know that the first coordinate is x coordinate. So we have 4 equals 2 plus 1 times lambda, so just lambda. Second coordinate is y coordinate, so 1 equals minus 1 plus 2 lambda, and third coordinate is z coordinate, so 0 equals 3 plus minus 2 times lambda, so minus 2 lambda. And from the first one we have lambda equals 2. From the second one we have that lambda equals 1. And from the third one we have that lambda equals 3 over 2. So as you can observe, this lambda is not the same as this lambda and as this lambda, and it means that our point P does not lie on L. Otherwise, the lambdas will be the same. Problem 2. Two lines in 3D are given by, and we are given L1 and L2. A. Determine where the two lines intersect. So if they intersect, they have to be equal at this point. So L1 has to be the same as L2, so our vector r has to be the same as this vector r. So also our right hand side has to be equal to this right hand side, because our r, vector r, is the same as this vector r, so it means that also right hand side has to be equal to this right hand side. So this is our equation, and now we have to take each coordinate. So our x coordinate is the first one, so 1 plus 2 times me, so 2 me equals x from the x coordinate from the second vector, so 3 plus 1 times v, so just v. Y coordinate is 2 plus minus 1 times me, so minus me equals 0 plus 2v, and z coordinate is minus 1 plus 1 times me equals 2 plus minus 2 times v, so minus 2v. And now we can simplify our equations. So these are our equations simplified, and in the second one and third one equation, we can observe that these equations contradict, because in here we have me equals, and here we have different values, and here we have the same values. So it means that we don't have v and me that can satisfy these both equations. That's why the lines do not intersect. B. Find the acute angle between them. So here we have to use our formula from the booklet, angle between two vectors, and it looks like this. And of course, in order to calculate our angle, we have to take the direction vectors, so this one and this one. In our numerator we just have to multiply and add each coordinate. So the first one is 2 times 1 plus minus 1 times 2 plus 1 times negative 2, and from this we have 2 minus 2 plus minus 2, so it's just minus 2, and in the denominator we have to just find magnitude of both direction vectors. So these are our magnitudes, and now we can substitute everything into our equation. So we have negative 2 over 3 times square root of 6. So we can either solve it in solver or rearrange it, so cosine to the power of minus 1 and in bracket negative 2 over 3 times square root of 6, and from this we have angle 106 degrees. However, we have to have acute angle, so we have to subtract from our 180 degrees this 106 degrees, and it's just 74 degrees. Problem 3. Two airplanes are flying at constant velocities. Plane A starts from position A0, 0, 0, 1000 meters and moves with velocity vector 200, 150, minus 20 meters per second. Plane B starts from position B0, 1500, 800 meters and moves with velocity vector minus 150 and 0 meters per second. A. Find the position vectors of both planes at time t seconds. And in order to do this, we just have to add our position vector to velocity vector, and in front of our velocity vector we have to include time. So our vector RA equals, and firstly our position vector, so 0, 0, 1000 plus t times our velocity vector, so 200, 150 minus 20. And for our second plane, we have 1500, 800 plus t, and our velocity vector is minus 150 and 0. And of course we can simplify our vectors. So in the first one we have 200 times t, 150 t, and 1000 minus 20 t. And in here we have 1000 minus 100 times t, 500 plus 50 t, and just 800. B. Show that the two planes never collide. So they will collide if at some point they are the same. So we have to check whether they are the same at some point or not. So in order to do this, we have to take our first coordinate from our plane A and equate it with our x coordinate from plane B. So 200 t equals 1000 minus 100 t. Here 150 t equals 500 plus 50 t, and the last coordinate is 1000 minus 20t equals 800. So now we can simplify our equations. So here we'll have 300t equals 1000, and dividing both sides by 300, our t is just 10 over 3. From the second equation, we will have 100t equals 500, and dividing both sides by 100, we have just 5, and in the last one, we have 200 equals 20t, so t equals 10, and as you can observe, this value is not the same as this one and this. That's why they never collide. Problem 4. Two lines are defined by L1 and L2, and in A we have to show that the lines do not intersect. So basically we have to do something that we did previously, so just equate each coordinate with each coordinate from both lines, because we have to check whether they are the same at some point or not. So first coordinate from L1 is 1 plus 2 times alpha equals, and third coordinate from L2 is 0 plus 1 beta. So 0 is just 0, so we don't have to write it. So just beta. And then we have our y coordinate, so minus 2 plus alpha equals 1 plus minus 1 times beta, so minus beta. And the last coordinate is 0 plus 1 alpha, so just alpha equals 3 plus 2 beta. And now we can simplify our equations and check whether 1 alpha and 1 beta satisfy these all equations. So from the first one, we have that beta equals 1 plus 2 alpha. From the second equation, we can move minus beta to the left hand side, so beta equals 1 plus 2, so 3 minus alpha. And the third equation is 2 beta equals 3 minus alpha. And as we can observe from the second and third equation, here we have our right hand side the same, however our left hand side is not the same, and it means that if at least two equations are different, like in our task, so that's why the lines do not intersect. And B, find the shortest distance between L1 and L2. And in here we have to use the formula that sadly is not in the booklet. However, sometimes it may appear, so it's good to remember it. So this is the fraction, and in the numerator we have and in bracket A1 minus A2, and in this bracket D1 times D2, and in the denominator D1 times D2, and the letter A is our position vector, and letter D is our direction vector. So we can also write them down. Okay, so firstly let's deal with A1 minus A2. So simply we have to subtract from our first coordinate from A1 the first coordinate from A2. So 1 minus 0 is just 1. Then we have minus 2 minus 1, so minus 3. And 0 minus 3, also minus 3. Now we have v1 times d2, so it means that we have to use our vector product. So now I will write down the formula for it. So this is the formula. So it will take some time because we have to multiply and then subtract many numbers. So first value v2, so it's our second coordinate from d1. So 1 times w3, so times 2, and then minus our third coordinate from v1, so 1 times -1. So this is our vector product with values substituted. So now we have to calculate it. So 2 minus 1, it's just 3. Then we have 1 minus 4 minus 3 and minus 3. And for the denominator, we have to find the magnitude of it. So our magnitude is square root of 3 squared plus minus 3 squared plus minus 3 squared. So we have 9 plus 9 plus 9. So square root of 27. So it's 3 times square root of 3. And of course, because in numerator we have a1 minus a2 and then we have dot, so it means that we have to use our scalar product, and it looks like this. So it's just this and this. So 1 minus 3 dot and 3 minus 3 minus 3. So it's 3 times 1 plus minus 3 times minus 3 plus minus 3 times minus 3. So it's just 3 plus 9 plus 9, so 21. And now we can substitute everything into our distance formula. So d equals, and of course in the denominator we have 3 times square root of 3, and in numerator we have 21, so it's just 7 over square root of 3, so it's approximately 4.04, and of course units. And that was the last problem from this topic, vector applications from geometry and trigonometry. And of course, if you found this video helpful and useful, you can leave thumbs up, subscribe to this channel, and in case of any questions, feel free to reach me out in the comments down below or via my mail. That is, as always, in the description of each video. See you!